Okay, so this lesson is 6.2 and 6.3. 6.2 begins on page 310. And if I were going to give this entire lecture a single title, it would be Centers of Triangles and the Segments That Make Them. There are 4 centers. 2 of them are in 6.2, 2 of them in 6.3. They should be in one section. If you have your phones out, put them up. Okay, the first one, and by the way, just a little comment here. We have entirely skipped constructions this entire time. You may have noticed that, maybe you didn't, I don't know. But in some of the lectures that are given before the exercises, there are constructions. I've completely dodged those. I have not given you assignments on constructions. If I inadvertently gave you an assignment, that was a construction. I said ignore it. A construction is something that you do that you make with a compass and a straight edge. You do certain things in a certain way, and you work 2 tools together and you're able to construct certain things. We have completely dodged that. And because of that, I'm not going to do the constructions that are required today because you won't know what they mean anyway or how they work. So I'm going to draw pictures and draw them as carefully as I can and show you what would happen had you learned how to construct things. It's not essential. It isn't to understand what's going on. So there are 4 centers of triangles and they are formed different ways and they do different things. They're important for different reasons. So I'm going to start out with the first one. And it's just going to take an arbitrary, generic triangle like that one. It kind of looks like a right triangle, and maybe it is, but I don't know. I don't mean it to. And what we're going to do is we're going to take a look at the perpendicular bisectors. We know what that is already from last section. And by the way, if you're watching this, I apologize for not recording 6.1, but it's fairly self-explanatory. These people handled it just fine. It's not that bad. So read it for yourself. If you still have questions, let me know. So perpendicular bisectors are the segments. These are the segments that are going to make a particular type of center. And because there are 3 sides, there are 3 perpendicular bisectors in this triangle, right? Okay. So perpendicular bisectors, I'm going to write imply or make, and we're going to come up with a name for it in just a minute, as soon as you see where they all cross. And I'll be honest with you, I really don't like this triangle. It's going to come up with something that I don't intend, so I'm going to have to draw it again. A different one. Like this. Okay, so we've got, that looks like, I mean, I think if we actually measure those, all the angles would be acute, and I don't know that all the sides would be different. I mean, that might be isosceles, but I don't mean it to be. So I'm going to say that this is an acute scaling. And I'm going to find the middle, and again, I would do this with a compass had we learned what constructions mean up to this point, but we haven't. So I'm going to pretend that. I'm going to find the middle of this and eyeball a line perpendicular to it. So that right there is the perpendicular bisector of the bottom side. I'll indicate that like this. Now, if I wanted to do that to this side over here, I would have to find the middle, and I'm eyeballing that. I'm going to say it's about right here. And I would draw a segment perpendicular to it coming out like this. And again, I'm just eyeballing it. If I were constructing it, it would mean something to you had we done constructions up to this point. But that's a perpendicular bisector of this side. And this one over here, if I find the middle of that side about right here and eyeball a perpendicular. Three perpendicular bisectors. And it is not coincidence that they all crashed in the same point. They always will. It's called a point of concurrency. Means they all share that point. Perpendicular bisectors will always share the single point where they meet each other. There will not be, it won't be like this and like this and like this. If that happens, the construction hasn't been done right, or I didn't eyeball it well enough. They are designed, if we did constructions, it would cross a single point all the time. And that particular point of concurrency formed by perpendicular bisectors is called the circumcenter. Do you know what this, it's Latin, do you know what circum means? That's pretty cool, Andrew. Andrew's back there going, it means, and he's drawing in the air, and he's exactly right. To circumnavigate the globe means to get in a ship and go clear around the globe. Circum means to go around. really, really weird too. Just as a comment on this. I don't know if you've ever seen it before, but sometimes they'll comment and they'll say, this story occurred about circa 400 BC. They'll use the word circa, and it means around. Around 400 BC is when this happened. They don't know the exact date. It's just around that. So they say circa. And actually, might put that in writing. So circa, and circa means to go around. And what that means is that this circumcenter right here that we named circumcenter is the center of a circle that contains all of these vertexes. So what we're saying here is, and I know I've already got a whole bunch of junk already in this, but what we're saying is that the distance from here to this corner is the same as it is from here to this corner is the same as it is from here to that corner, because they're all radiuses of a circle that contain the corners. So a circumcenter is the center of a circle that goes around the triangle containing its vertexes. And you can find a circumcenter by finding the perpendicular bisectors. Now, since it's guaranteed they will all crash in the same point, it's not really necessary to find all three if you're careful. If you've got a triangle like this and you want to find the circumcenter, you really only have to find two perpendicular bisectors, that one and maybe that one. This will be the circumcenter because the other one will crash there. That's a really poor drawing, but you only need two because the third one's guaranteed to do the same thing. Okay. So this is what I want you to really come away with. I want you to know what a circumcenter is, it's the center of a circle that contains the vertexes, and it's formed by perpendicular bisectors. You have to come away from this section knowing this fact and what a circumcenter looks like. A side note or a corollary is that if you find the circumcenter, it is the same distance from that point to every corner of the triangle because they are radiuses of the circle. Does this make sense? It's the same distance from the circumcenter to each corner. And that can be useful if you've got, say you've got some sort of a big plot of ground and you're going to make a park out of it. Kind of like this one out here that's kind of a triangle. The one that's out here in the corner. If you wanted to put something, some sort of fountain or some sort of a monument or whatever, that was the same distance from each corner, you'd have to find the circumcenter. Okay? All right. So that's the circumcenter. It's formed by perpendicular bisectors, and you have to know that these kind of segments make this kind of center and what the center is. Next one. If I have a triangle, plain old generic triangle again. Oh, there's something out about circumcenter, so I haven't finished. Sorry, we're not ready to go there yet. Wait. Think about this with me. If we have, that was an acute triangle. If I have a clearly obtuse triangle, and I find the perpendicular bisectors. I'm going to do this kind of fast. I'm going to eyeball it. I find the perpendicular bisectors. It's not quite right. About right there. This one right here. The circumcenter is outside the triangle. It doesn't have to be inside. What that means is that your circle looks something like this. Sorry, that's really crappy, but that's what it means. It's still the center of the circle. It just happens to be outside the triangle because it's obtuse. Now watch what happens if we looked at an acute one and the circumcenter was inside. We looked at an obtuse one and the circumcenter was outside. What do you suppose will happen if I have a right triangle? And I drew the perpendicular bisectors. That would be this one right here. And this one right here. I didn't draw that very well, but this one right here. Like this, and this one right here, they all have to hit the same place. They hit right smack in the middle of the hypotenuse. What happens? Because by drawing these two right here, they have to be perpendicular. Two sides that are perpendicular. So you got a rectangle right here. That's the midpoint because I went exactly halfway up and halfway out, and they crash at the midpoint of the hypotenuse. Because this perpendicular bisector also has to cut that in half. So on a right triangle, that's another thing you need to come away with. If it's obtuse, the circumcenter is outside. If it's acute, it's inside. If it's a right triangle, it's on the hypotenuse right smack in the middle of it. It might be a nice note for you to take because they'll be drilling you on that a little bit. Okay. So the circumcenter could be in, out, or on. And you have to know where the on one is and in what circumstances. Okay, Perpendicular bisectors make circumcenters, and that circumcenter could be in, out, or on. And if it's on, it's in the middle of the hypotenuse. Probably right triangle. Okay, now I'm ready to move on. Next center is formed by a different set of I'll start with an acute triangle again. That looks like a right triangle. I'm going to pretend this is 89 degrees, okay? This one now, what we're going to start with are the 3 angle bisectors. Angle bisectors mean all 3, and there's 3 angles here. It means we've got segments which come out of each angle and cut that angle right in half. So I'm going to try to make that split right in 2 like that, where this angle equals this one. That's an angle bisector for that angle. The angle bisector for this angle looks like that, and the angle bisector for this angle like that. And again, there's a point of concurrency. Now, I didn't divide that one very well. This is what I get for freehanding it or eyeballing it, but we're going to pretend. And if this actually were true, and I actually constructed it, they would all crash in one place, this thing right here. And that was formed by making all 3 of the angle bisectors, and they will all hit in a point of concurrency called the in center. Circum means to go around. In means inside. So this is the center of a circle that just snugs up against each side as it comes around. It's the center of a circle on the inside. Pretty crappy drawing. So if you bisect every angle, then the place where they meet will be the center of a circle, and that circle will be one that just snugs up against each side. In other words, it's a circle inside. Now, do you think that we could construct, or can you think of a triangle where the center of the circle that's inside the triangle is outside the triangle? You can't have the center of a circle that's inside a triangle have that center be outside the triangle. Can't happen. So an in center will always be inside. You remember that because of the word in. This will always be inside. I don't care what kind of triangle it is. If we drew an obtuse one, it's clearly obtuse, and I bisect each of those angles, you can see that it's going to be inside no matter what. You do a right triangle, and I bisect that angle, and that angle, and that angle. It's going to be inside. Okay? So the in-centers are always inside because they are the centers of circles that are inside. But it's angle bisectors that make them. And you've got to come away from this exercise knowing what kinds of segments, angle bisectors, make in-centers. You got to know the perpendicular bisectors make circumcenters. That's section 6.2. Let's take a look at a couple of examples before we move on. Take a look at example 1 with me on page 311. This is kind of silly, but listen to what it says. 3 snack carts sell frozen yogurt from points A and B and C outside a city. Each of the 3 carts is the same distance from the frozen yogurt distributor. So inside that city, somewhere inside that city is a frozen yogurt distributor, and they're saying that each one of those is the same distance from the distributor, each of those snack locations. Find the location of the distributor. Which one of these would you use? This one, because if you find the circumcenter, they are the same distance from the corners, and the snack carts are at the corners. If you want to find a point that's the same distance from every corner of a triangle, it has to be the center that makes this circle, since each of these blue pieces is a radius. You'll notice, and I realize this is a really crummy drawing, but the distance from here to here is not necessarily the same as the distance from here to here. It is the same distance from here to here and here. No, it isn't, because that goes to a corner. Maybe those radiuses are the same. But okay, here's the problem with that scenario right there. Even if these are the same, and I think they are. If those 2 things, not this one. If these 2 things are the same, and I take this one out perpendicular to that side right there, these would be the same, but they're going to the sides of the triangle, not the corners. And these snack carts are the corners. The corner is the same distance from something. It has to be the circumcenter. These are each the same distance from the sides, perpendicular to them, But those snack carts are not on the sides of the triangle, they're the corners. So, moving on, let's see if we got any other cool examples for us. Look at example 3. This one has to do with the end center on page 313. Page 313, right at the top, it talks about the theorem, which is the end center theorem. I just drew that for you. Then it says, using the end center of a triangle. Now, this one you are going to have to do. You want to pay attention to this one. Okay? You look at the figure while I read this. Can you see that BN, AN, and CN are all angle bisectors? They're all red. You see that? And so where they meet at N is the center of a circle inside that triangle. But what about NE and ND and NF? They are not parts of the angle bisectors, right? They're these ones that I drew here and kind of made a mess of it. But they're these kind of segments that go directly from the center to the sides as quickly as possible, making them perpendicular. Those are all radiuses of that circle, and they are all the same. The perpendicular ones are, the blue ones, because they're radiuses of a circle. And radiuses are always the same. Okay, so here's what they're telling us in the problem. They're telling us that ND, everybody find ND. Did? Is it blue or red? Is it perpendicular or not?
Yes.
Perpendicular. So it's a radius of the circle inside. So ND is a certain thing. NE, you all find NE? Is it an angle bisector? No. Is it perpendicular to the side it is?
Yes.
Then it is a radius of the circle that they didn't draw, which means that ND and NE have to be equal because they're both radiuses of this circle inside. Do you understand what I'm saying? Radiuses are always equal. So we set them equal to each other. And we find that, if you see in the solution there, we find that x equals 4. But they're asking us what NF is, for heaven's sake. Well, NF is another radius. So once you find out that x equals 4 by solving that equation, go find either NE or ND because it'll be as long as NF. So if I find ND, it would be 4 times 5 minus 1 is 19, so NF is also 19. You see what's going on? Those are all radiuses. If they're perpendicular to those sides, they are radiuses of this circle, and radiuses in a given circle are always the same length. And then it says in B, can NG be equal to 18? NG, everybody find NG. Can NG be equal to 18? No, because it's longer than NF. It's not perpendicular, so it's longer. And NF was 19. Moving on. Okay, so we're done with 6.2. Moving on to 6.3. That's why they should be in one section. 6.3's title, if you see on page 319, the title of it is Medians and Altitudes of Triangles. Turn to page 320 is where we start on this. I told you there were 4 centers of triangles. We've discovered 2. Circumcenter, center of a circle on the outside. Incenter, center of a circle on the inside. There are other things as well. And before I need to describe to you what medians and altitudes are. So if I just draw a plain old generic triangle again of any particular type here, if I ask you to draw the median from B, here's what you gotta know about medians. They always start at a vertex. Medians always contain a corner. And where they go from there is the middle of the opposite side. So they're not necessarily going to bisect an angle, but they are going to bisect a side. If I know that's the point, which is the middle of AC, then the median starts at B, the opposite corner, and goes to that. That is a median because it bisects the side that it comes from. Bisects the side that it hits, and it comes from the opposite corner. Notice that the angles are not bisected. It's the side it hits that's bisected. That is a median. Median. Got it? Because there are 3 corners, there are 3 medians. So if I find this point right here, which is the middle of this one, and start at the opposite corner C and connect the 2 points, that's a median also. And the median from here would bisect this side in half, about right here. So the opposite side gets cut in half, and we go from A, the opposite corner, to that, and again, I'm freehanding, they all will meet at one point. So medians, if you remember what a median is, always starts at a corner and goes to the middle of the opposite side. That's a median. And medians, when you draw them all, always meet at a point of concurrency called the centroid. A centroid is a center of gravity. What I mean by that is, if I made this triangle out of wood, wood is not dense. It doesn't have an equal density all the way through it. Some pieces are denser than others. But if I made this out of a solid piece of plastic that was really rigid, maybe a 1/4 inch thick, and I made it out of solid plastic, and I found this extremely carefully, I found this right here, I would be able to balance it on the point of a compass. And it would balance. It would sit there if I was holding it really still. I mean, if you could hold your hand still enough. It's a point of balance for anything that has any mass at all. You guys have mass. I have mass. Guess where your center of gravity is? It's not your centroid because that belongs to only triangles. But a centroid means a point of balance. Guess where your centroid is at this stage in your life? Right at your belly button. Guess where the centroid is for kids that are just learning to walk? Kids that size. Yeah, up here. Why? Because they've short. Because their heads are and heavy. That's why. I mean, how many of you have T-shirts that have snaps on the shoulder so you can get it over your head? Toddlers, that's the way you buy them, so that you can get the hole big enough to go over the big fat head and then snap it up so it'll stay on and look right instead of hang off. They have enormous heads compared to their bodies. Your head doesn't grow as fast as your body, and so you grow into your massive head. And their center of gravity is up here. A lot of people think that when you walk up to a toddler that's just learning to walk and give them a little push, the reason they fall over is because they're not good at walking. No, it's because they're so top heavy. You give them a little shove and they just... Luckily, they're close to the ground and generally have a diaper on. It doesn't hurt them. But I've got a little one like that. He's just barely more than one. He's learning to walk really well. He's actually learning to run. But boy, it doesn't take anything to get him over. And it takes a snap shoulder T-shirt to get him dressed. So as you grow, your center of gravity migrates down to here until you're nearly adults like you guys. It's centered right at your belly button, which is where it should be for walking and doing all sorts of things like gymnastics and things like that. It's nice that your center is in the center. So that's what a centroid is a center of gravity for a triangle. So this is specific to triangles, whereas this is more generalized to all sorts of physical things. But a centroid is a point of balance. It's not the center of any circles. Do you think that you could come up with any triangle whose centroid is not in the triangle? Now that you know what a center of gravity is. No. You can't balance things on a point that's outside them. You can't set them on it. It's dumb. So a centroid is always inside. Always. Centroid will always be inside the triangle, and it will be a point of balance. So this is a balance point. It's kind of interesting because where this might be, that's horrible. It looks like BAC, balance. Okay. Because there was an experiment one time at the INL. Engineers were out there working. They're old guys, older. And they had a group of high school kids that came as interns for the summer. And they were trying to find out a good place to put a power plant on a river so that it could feed power to 3 different cities that were not on the river. And they wanted to find a place on the river to put it so that they would have to build as few power lines to those cities as possible. They needed to do that. They needed to have, if all the cities were the same size, they would need a circumcenter, right? Because they'd all be the same distance from the center for the city. But the thing is, the cities were different size, and so you'd have to string more wire to one that was bigger, and that would cost more money. And so you would want to place the power plant a little closer to the bigger city. Man, they were trying to figure that out. They couldn't do it. They were trying to figure all these things out. And what these high school kids did was they built a map, and they put a city at each of these locations, and they straightened the river out pretty well. They put the river on one of these guys right here, which was about where the river was, approximately. And then they put a weight on a string. They drilled a hole in the board where the cities were, and they put a weight on the string equal to the relative size of the cities and the power they would need. And they tied the strings together, and they held them, they dropped it through the hole, and everybody held it up, and everybody just dropped the size of the city down like that, and that thing scrolled along the river and landed right where it should be, according to the weights of the cities. I thought that was a very novel, very, very cool solution. But what they were looking for was the point of balance for the triangle in the cities. And it didn't occur to those old guys who were set in their ways that it was something as simple as that. And they were able to find it just like that. And they got an award, they got a lot of money, they got scholarship money and everything because they were able to think in a novel way. These old guys, they couldn't do it. And it wasn't that hard to design. It was very cool. But they were looking for the centroid, not the circumcenter, because the weights of the city were different. The point of balance was somewhere else. You know what I'm saying? So centroids can be very valuable as for triangles and like that as well. Okay, now take a look at, I want you to, even though it's not an example, I want you to look at the monitoring progress in the middle of page 321. It's got the picture of a park and some roads going around it. Page 321 says, there are 3 paths through a triangular park. Each path goes from the midpoint of one edge to the opposite corner, meaning they are medians. These are medians, these sidewalks. The paths meet at point P. And then it says this, find PS and PC when SC is 2100. Oh, wait a minute, I forgot to tell you. We can't do that yet. Hang on, come back to this. Hang on, I forgot something. Hold on, I forgot to tell you something really, really, really cool about centroids besides being a center of balance. When you draw all 3 of these, they split each other up. All 3 of them split each other up at this point right here in a ratio of 2 to 1. 2 to 1. So what I'm saying is on this one, if this is now, these numbers aren't going to match up with the lengths, but if this were 2, I could guarantee that this was 1. If this was 9, I could guarantee that this was 4.5. Don't sucker for it. This has to be twice as long as this, so that all 3 parts together make up the entire median. But they are split in a ratio of 2 to 1. The long part is twice as long as the short part. You with me? So if I told you that AD was 15, how long would this part be? 10. And this one? 5. So I could tell you the full length. You split it up into 3 parts and give 2 of them to this one and 1 of them to this one. Or if I told you the short one, you would double it for the long one. Or if I told you the long one, you'd cut it in half for the short one. It's a ratio of 2 to 1. All the segments are that way. Okay? Now, let's go back to this. We're convinced that the center of that thing, the center of this park, is a centroid center. And it says find PS and PC when SC is 2100 feet. SC is the full length. How long is SP? How long? 700. How long is PC? 1400. Who's not following? You see where we're getting those numbers? Okay, look at the next one. Find TC and BC if BT is 1,000. So we got to look at those. We'll find TC. TC, BC is what we want to find. TC and BC. Okay. If BT is 1,000. If BT is 1,000, then how long is TC? 1,000. Because we're talking, it's the middle of the side where the median meets. And so how long is BC? 2,000. Okay, so we're talking about the bisector part of this now. It's not a 2 to 1 ratio, it's a cut in half thing. All right, so if PT is 800, find PT. You see PT? If PT is 800, then how long is TA? No. How long is PA? 1,600. And how long is TA? 2,400. You see the relationships? Okay, so what they're trying to drill into you folks is that if you're talking about the sides, they are cut in half. If you're talking about the medians, they are cut in a ratio of 2 to 1. You see what I'm saying? Yeah? Okay. That's another cool thing about centroids that you can guarantee. All right, the last center is made from things called altitudes. So again, let me draw a triangle. I'll show you what an altitude of a triangle is. You guys know what the altitude of an airplane is?
Yeah.
What is it?
It's the height relative to the ocean.
You're right. It is. It's a ground zero, meaning sea level. Does it mean that? Does it? I think in relative terms that the altitude of an airplane is the distance from it to the ground at any given moment. And the ground can vary and the airplane can stay solid. But the pilot needs to know how close he is to the ground. Relative to sea level, that's a different thing. That's an altimeter. That may be an altimeter reading, but the altitude, it may be the same. I got to think about that. But an altitude is from the ground to the airplane so that he knows how much space he's got for safety, right? So and it's right straight down. So for example, if you've got the ground down here and it's going like this and the ground is up and down, I don't know if it would be like that. You got the airplane right up here. This is his altitude, not this and not this back to the airport or this over to the next airport. It is right straight down. And it's like he's dragging a perpendicular stick along with him like that. And the length of that at any given moment is altitude, right? And the perpendicular stick is the operative word here. Right to here, we're talking about this distance and it's always perpendicular. So an altitude in a triangle goes from a corner just like a median does, but it hits the opposite side in such a way that it is perpendicular to it. That is an altitude of a triangle. It always starts at a corner just like a median, but it goes directly to the opposite side with the shortest distance possible, which means it is perpendicular, like the altitude of an airplane. Are you with me? We call them altitudes. And because there are three corners, there are three altitudes. So if I draw it from this corner right here and head perpendicular to this one, that takes a little bit of skill. You might want to use a ruler. It comes up here like that. About that looks about perpendicular to me. And if I drew the same one here to the other side perpendicular to it, that's not a very good perpendicular marker. Perpendicular to it, they will always crash in one place as well. This point of concurrency when they are made with altitudes is called an orthocenter. That's a hard one to remember. Altitudes, you got to know what an altitude is. They always start at a corner and they go to the opposite side perpendicular to it. Altitudes, when you draw all three of them, make orthocenters. And the only application I can think of an orthocenter, there's probably many, many more, but the one that I can think of that works all the time is if you're out on the ground, out on the desert someplace or something like that, and you've got a seismograph. You know what a seismograph is? Detects vibrations in the earth from earthquakes. You got a seismograph there and one here and one here. Then if an earthquake happens you can gather information from an earthquake. And if it hits all three of these things, and you can see how long it took for the waves to arrive at these seismographs and the intensity of them, you can do what's called triangulating and figure out the epicenter of the earthquake. If you gather information from these three seismographs, if they're located here, here, and here, and form a triangle, and they all receive intensity and wave distance information from them, you can take all of those and triangulate the epicenter. Now, what if your seismographs are located something like this? Let me make that a little bit longer so it's very clear that this is obtuse. I need to draw that differently or I'm not going to have enough room on the board. I forgot how this works. So hang on a minute. Let me draw another one. Let me draw it like this. Obviously an obtuse triangle, right? The seismographs are located here, here, and here. What I'm saying is the epicenter of the earthquake doesn't have to be inside the triangle. It is if it's acute. But watch what happens as I try to draw the altitudes for these. Drawing this one isn't very hard. So we eyeball and we say, I'm going to go right straight to there. There's that looks perpendicular. And then you try to draw the one from this corner and you're headed towards this side. And you imagine any possible segment. If you go to here, that's not close to perpendicular. Or here, I'm getting closer, but I draw that right there and I'm still not perpendicular because this is obtuse. So watch this. This is tricky. You have to extend the side that you're trying to get to with a dotted line because it's not part of the triangle and draw it to that. That is an altitude from that corner because it's drawn from the corner perpendicular to the line containing the opposite side. Are you with me? So to do this one right here, if I have to start at this corner and head towards that side perpendicular, going right there is about as close as I'm going to get if I'm going to stay within the triangle and try to hit that side. I'm never going to hit it because it's obtuse. I have to extend this and go from there, perpendicular to the line containing it. So where the heck is the orthocenter? Well, it is, if we extend these, right, this is going to be pretty crappy, it's right there. So if you have seismographs located on an obtuse triangle like this one here, here, and here, we can triangulate the epicenter to be way back here. Because these all receive signal information from the vibration of the earth, and we can take those things we get and figure out right where the earthquake was. But the orthocenter here is on the outside, just like the circumcenter was on the outside of an obtuse. Now, if you'll remember the circumcenter, this is just a little bit more information. If you remember the circumcenter, when we drew the perpendicular bisectors, was kind of in the big obtuse. If you extend that big obtuse angle out, it was inside there. This one isn't. The obtuse angle comes out like this. It's always behind, what I consider behind the triangle, the orthocenter. It's outside it, but it's behind it rather than within it, within the range of that obtuse angle. It's behind the obtuse angle. So the other condition we have to consider is what happens if we're talking about a right triangle and we want to find the orthocenter. Where will that be? Well, if I draw the line, that's the right angle right there. If I draw it from this corner perpendicular to that side, that's not too hard to do. It's right there. But what about the one from here? How am I going to draw it to the opposite side? It is this side. See it? And if I draw it, the one that goes from this corner to this opposite side, it is this side. So where's the orthocenter? At the right angle corner. That's where all three of these meet. The altitudes all meet right at that corner. So if you've got seismographs here, here, and here, this one probably won't register because it's probably busted. It's right at the epicenter. So orthocenters can be in, on, or outside, depending on the acuteness, rightness, or obtuseness of the triangle. Are you with me? So orthocenters and circumcenters can be found in, on, or outside the triangle. Centroids and incenters have to be inside. And altitudes make these. Altitudes, you have to know what an altitude is. If you draw all three of them, you will have where they cross. The concurrent point that we have will always be the orthocenter. Orthocenters are made from altitudes. You gotta get that straight. Look at example 4, please. Example 4 says, now we're going to do a little bit of a proof, although it's not going to be a formal one. We're going to take a look at it. It says, prove that the median, now what a median is, goes from a corner to the middle of the opposite side. Prove that the median from the vertex angle to the base of an isosceles triangle is also an altitude. Now we got all these words and all this vocabulary. We're trying to see if we can figure that out. So we have an isosceles triangle, and we're going to draw the median from the vertex angle to the base. It's got to be isosceles first, so I know this. Since it has to be isosceles, I know that. Boy, that's a crappy one. Hang on. Try it again. That looks equilateral. Hang on. I'll get it. Make this one a little bit skinnier. So they're saying we're going to draw a median from the vertex angle of an isosceles triangle. So since that's all given, I know this equals this. This is the vertex angle. I'm going to draw the median, which means that's going to cut this in half. I want to prove that this thing that I drew is also an altitude. Well, aren't these triangles congruent? Side, side, side. Can you see it? Yeah. Doesn't that make this angle equal to this one? Yeah. And since these are both on a straight line, they've got to split 180 evenly, making them 90, making this a right angle, making this an altitude. Okay? Not only that, because these triangles are congruent, this thing is also an angle bisector. CPCTC on those two angles. So this thing that was started out just being a median ended up being an angle bisector, an altitude, and not only that, because it's an altitude and bisects this, it's also a perpendicular bisector. All four of the segments we've talked about today, that guy right there is. It's an angle bisector, see those? It's an altitude, see the box? It's a perpendicular bisector because it's not only perpendicular but cuts it in half. And it's a median because it starts at a corner and cuts the opposite side in half. So that segment is all four at once. Not only that, and this is kind of cool, if you have an equilateral triangle, which is also isosceles, meaning any one of these could be the vertex angle. If you draw this and this and this, that point of concurrency in an equilateral triangle where this is the same length as this is the same length as this, that point of concurrency is all four of them at once. It is a circumcenter, it is an incenter, it is a point of balance, and it is an orthocenter because all of these have to be perpendicular. So in an equilateral triangle, the point of concurrency, all three of those segments are all four things at once, and the point of concurrency is all four centers at one time. Okay? Equilateral triangles are very cool.
How would you write that in proof?
You wouldn't. Did they want you to prove it in here? I mean, we could do it, but it would take forever. It would be like 15 steps long, because you have to prove each one of them in a separate piece of it. Did they want you to do that? Thank goodness. I'm just saying that that's the way it turns out. You could prove that this triangle equals this one, 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 and get all of their parts and prove all of these things you wanted to about all of those centers using CPCTC. So without proving it, you're going to take it on faith, but it seems to make sense. It's a point of balance. It's the center of a circle outside. It's the center of a circle inside. And it's an orthocenter too because all those are perpendicular. All of them at once. Okay. Alrighty. So that's the extent of 6.3 to turn page. There it is. Now I want to give you both assignments. On 6.2, these are separate assignments. You get credit for both of them separately. So on 6.2, the assignment goes from 3 to 7, 9, 11 through 16, 35, and 36. That is not a very long assignment.
What's the first number?
3 through 7. Then on 6.3, separate assignment. It is, hold on, 1 through 14, 30 to 36, 40, 41, 43, and 48. Sorry, what?
Can we look at our test?
Yes, in just a second. I got one more cool thing to tell you about Centroid. Okay. Here's what's really, really cool. I'm not sure that they're going to test you on this, but it's another fact that's really nice about Centroid. If I've got for example, I'm going to make these easy to work with. But if I've got, those of you watching this, let me go over here so you can see the grid. This is another cool thing about centroids, and it's going to be hard to see because you're at a funny angle, but what I'm saying is if you have a triangle, let's say that one of its vertices is here, and one of its vertices is here, and the other one is, let's say, right here. The centroid, mind you, the centroid's location will be the average of the x's, comma, the average of the y's. Very cool. So this is 1, this point right here is 1, 5. This point right here is 2, 2. And this point right here is -5, -1. So what I'm telling you is that the location, without actually drawing all of those segments I taught you about, the location of the centroid will be 1 plus 2 minus 5 over 3, comma, 5 plus 2 minus 1 over 3. You can figure that out. That will be the location of the centroid. Now let's see, that's 3 minus 5 is negative 2, so it's negative 2/3. And this one will be 5 plus 2 is 7, minus 1 is 6. 6/3 is 2. Let's see what that is. Negative 2/3 is about right there, and positive 2 is up about right here. I'm claiming that that's the centroid. So if I draw the medians, it's reasonable. The average of the x's, comma, average of the y's will be the actual location of your centroid if it's on a grid like this. It's kind of a cool thing to know. Don't forget, centroids split those 3 segments up in a ratio of 2 to 1. I'm going to drill you on that a little bit. Okay, what was the question? Somebody asked me a question, and I said, wait a minute.
Look at it.
Oh, look at yourself. Yeah, we got 15 minutes, we can do that. There you go.